Alright, I think it's high time for some magic. I'm not a huge fan of the half-angle identities. I guess I am. I don't know. I know them by a different name. I know them by the power reduction formulas, and that's something that we do in Calc BC. So I'm going to save that for there. But you might write it down in your notes here that to me these are the power reduction formulas. Part of the reason that I don't exactly have these memorized is I can get them from somewhere else. What I'm going to ask you to do is think about one of the double angle identities. I want you to think about one of the cosine 2x ones. There was one that we had that was said the cosine of 2 theta was equal to 1 minus 2 sine squared theta. And I want us to do something interesting here. Let's solve this for the sine of theta. Right? So what I'm going to do is I'm going to sort of subtract some things around. I'll get the cosine of 2 theta minus 1, I guess, over negative 2 equals sine squared theta. That left side is kind of messy, so I'm going to reorganize that. I'm going to make it 1 minus cosine 2 theta all over 2. Right, I just like switch the order at the top and sort of factor the negative at the bottom. This gives me sine squared theta, and then I can just square root both sides, and I end up with sine theta equals plus or minus the square root of 1 minus cosine 2 theta all over 2. The question is, do you see what I want you to see? Right? To me, this is the same as this. In some sense, the only difference is the relationship of the angles here. And really what it boils down to is when they call them the half-angle identities, they say, hey, if you want to know half of what theta is, like that would be theta over 2, just put theta over here. In this one, they're just saying, hey, if you know what 2 theta is, well, you can find out what half of that is. So part of the reason that the half-angle identities aren't memorized to me as half-angle identities is I really see them as coming directly from the double-angle identities, which have a lot more use to me. So take that for what it's worth. The half-angle identities are not given on the IB exam, on the IB formula booklet, which means they're probably not extensively tested on the IB exam. Like on the Calculus BC exam, they tend to not ask about half-angle identities. They do ask about the power reduction formulas, but we'll get there when we get there. So long story short, I don't really feel like these need to be explicitly memorized, but I wanted you to be aware of their existence. I want you to know about these things and know that they exist so that you can use them and you can sort of refer to your formula sheet when you need to. So with all that said, I've got an example here. I want us to use the half-angle identities to compute the values of the sine of 75 degrees and the cosine of 15 degrees. We've done these problems numerous times. I just wanted you guys to get a chance to use the half-angle identities to actually do that. So our half-angle identity for sine says that the sine of theta over 2 is equal to plus or minus the square root of 1 minus the cosine of theta all over 2. So now the question is, what do I have to use as my theta here if I want to figure out what 75, like the sine of 75 degrees is? And what we're going to do is we're going to end up using 150 degrees, because half of 150 is 75. So this will give me plus or minus the square root of 1 minus the cosine of 150 all over 2. And now I just have to evaluate that. So let's see, 150 degrees. 150 degrees is way over here. So the cosine of that looks like it's negative root 3 over 2. So I'm going to get 1 minus negative root 3 over 2, so plus root 3 over 2, all over 2. And note, the formula here says plus or minus. Which one is it going to be? Well, if I'm getting the sine of 75 degrees, 75 degrees is over here. I know that that's going to be positive. So we're going to go with the positive square root. This gives me the square root of, and we could simplify this on the inside a little bit. I'm thinking if we were to multiply the top and the bottom of this fraction by 2, if you do that, you'll end up with 2 plus the square root of 3 all over 4. And so it looks like I can write this as the square root of 2 plus the square root of 3 all over 2. And this is our answer for what the sine of 75 degrees is. That's interesting. I could ask you guys to compute the cosine of 15 degrees now, like use the half angle identity for cosine, but to be honest, we've done that problem a few times now. Um, I think we know that we're going to get this same thing. What's maybe more interesting is when we did this problem earlier, when we used the angle addition identity, we found that this was the square root of 6 plus the square root of 2 all over 4. And so the question, and I think the thing that would be a more interesting use of our time is, are these two things really equal to one another? Right? And so I would challenge you guys to think through that. Like, see what you can come up with here. See if you can justify or come up with a reason for why these two things should be equal to one another. So pause the video, work through that. So what I'm going to do is I'm going to, and I want to be careful about this, I'm not going to square both sides of the equation, because to me this isn't an equation. Like this is, and this is going to sound silly, but this is an equation question mark, which is not an official mathematical symbol, but it's sort of like, I don't know if these two things equal to one another. So independently of one another, I'm going to do things to them and see whether or not they end up the same. So when I square each of these, when I square the one on the left, I end up with, it's sort of a fairly simple thing, I end up with 2 plus root 3 on the top, because when I square the top, the square root just goes away. On the bottom, I have 4. On the other one, when I square it, I'm actually going to have to FOIL the numerator. I'm going to have to do the square root of 6 plus the square root of 2 times the square root of 6 plus the square root of 2. And it's all going to be divided by 16. But that's okay. I mean, we're hoping to see something here, so we'll see what happens. When I FOIL together the top, I end up with 6 plus 2 root 12 plus 2, and this is all over 16. See, if I combine like terms, I get this is 8 plus, and then we can actually simplify this root 12 here. I can turn that into 2 root 3, so all in all, I'm going to end up with 4 root 3 there, divided by 16. And now, because all three of those things share a factor of 4, I can divide 4 out of that, and I will end up with 2 plus root 3 all over 4. So sure enough, these two things are equal to one another, and because of that, these two answers that I got are equivalent to one another. So while they're different, they are both correct. Neat. I don't think I was expecting that. Hope that was fun.